Hi, and welcome to this Lesson 8 in our Lessons for Beginner Machinists. Now, this Lesson 8 is going to be all about drill presses. But before we get into that, I'd like to explain a little bit about where this is going. Why should we look at where it's going? Well, because I'd like to explain a little bit about the objectives of all of my videos, except for the jokes. Now, my videos, or I produce videos for novice machinists, and what I really am trying to do here is get a package together, something that could help a novice, someone who's just starting out in machine shop. Maybe that person has a lathe in their garage, or a drill press, or a pedestal grinder. They're just starting out and they'd like to know a little more about how things work in a machine shop and how to go about producing parts. Well, that's what I'm shooting for. And in my lessons up to now, because I have 4 types of videos, now the first type is the jokes, and that really has nothing to do with the shop, but in the 3 other types, I have my project videos, I have my little quickie videos, which are video answers, and I have my lesson videos. And they all kind of work together, but it's all a little mixed up and hard to follow. So with this first video, theory video, the Lesson 8 video, that's going to relate or pertain to a machine tool specifically in a theory type of course, well, we're going to be looking at drill presses, and we're going to explain the whys and the wheres of drill presses. But because we have other types of videos and we've had other lessons, well, it's not going to be as long as you might think it could be. And that means that I'm going to be referring a lot in this video to other videos that I've already produced. And I'll be posting links in this video to get you to those other ones. And if you haven't seen them, well, it'll get you up to date on everything I've been working on. I would also like to mention that I've received, not many, but a fair amount of comments relating to the sound quality in my videos. Well, I hope that the sound is getting better, but you have to remember, this is real amateur video here, and this is something that I really just do for fun. It's a one-man show, there's no one else around me here, I do it all on my own. So sometimes there's quality issues. I'm not really someone who's knowledgeable about producing videos, so I'm sort of learning as I go. And also I get comments about the fact that the videos aren't in high def. And I understand that today everything is in high def, but believe you me, I've said it before and I'm going to say it again, you do not want to see me in high def. I really don't look that good. I mean, I'm at that age where I won't even walk around shirtless in the yard in the summertime anymore because it confuses the children. So let's get to our Lesson 8 on drill presses. And as you can see here to my right, well, I have a small benchtop drill press. And if we look over here, my assistant and presenter, the charming Mark, will be showing you a larger, about twice the size, a larger desktop or benchtop drill press. And charming Mark will also be showing you on the other end of the shop my combination mill and drill. So why talk about these 3 different machines now? Well, because I want to start by talking about size. And in the machine shop, when it comes to machine tools, well, size does matter, but probably not for the reasons that you think. Now, I'm a pretty big guy. I'm close to 300 pounds. Now, note that I didn't indicate whether I was close under 300 or close over 300. But I'm just going to stick to saying that I'm close to 300 pounds. And one thing that I know by experience is that big guys don't move that swiftly. But once we get moving, we're hard to stop. Well, it's the same with machine tools. Smaller machines can reach higher RPMs and can be used because they can work more delicately. Large machines, well, are made to apply large amounts of force to a part, but can't easily cut with small tools. One of the biggest mistakes that novice machinists make is to use the improper speed for the cutting that they're trying to accomplish, or to use too much or too little pressure on the cutting tool. Now, if we recall, our formula for calculating RPM, well, was cutting speeds times 4 divided by diameter. That's the imperial formula. Cutting speed, well, varies from material to material. Each material has its own cutting speed. Mild steel, as an example, has a cutting speed between 100 and 120 surface feet per minute. Times 4, well, that's a constant. Divided by diameter, diameter of what is turning. If you're on a lathe, it's the part. If you're on a drill press, and that's where we are now, well, it's the diameter of the tool that's in rotation. Now, I'm not going to get into that formula any more than I have to, and I'm not going to get into the metric formula, which is quite similar, because we have a full-blown video on that subject, and here's a link to that video if you want to freshen up on cutting speeds and how to calculate the proper RPM for the job at hand. Now, that formula is linear, and that means that everything's proportional in there. So let's say we had calculated that for a 1-inch drill, we're going for a certain material, I don't know which one, we're just going to use round numbers here. We calculate with the formula that an RPM that should be around 400 RPM, let's say, just imagining things, for a 1-inch drill. Well, if I were to use in the same material a 1/2-inch drill, I would double its RPM. So for a 1-inch, I'd have 400. For a 1/2-inch, I'd have 800 RPM. If I half that again, I'd end up with a 1/4-inch drill, and it would have to turn at 1600 RPM. And if I half that again to a 1/8 of an inch diameter drill, well, I'd double the RPM again to 3200 RPM. So we can see that the RPM increases rapidly, okay? When we get into small drills, the RPM is incredibly high. And that's why we need different types of machines. And remember, it's for 2 reasons. We need a high RPM. To get high RPM, we need small machines. And we need delicate cutting pressures. For delicate cutting pressures, we need small machines. You can't use a huge drill press with a huge handle and a great leverage and expect to be able to drill a 1/16 of an inch hole. You're going to break the drill. You cannot apply the proper amount of pressure. You're always going to be applying too much pressure, irregardless of the RPM. So we can see that different sized machines are important. If you take a look down here, just next to the foot of this little benchtop drill press, you'll see that there's a nice drill index. And everything on that drill index seems normal until I pick it up. It's a tiny drill index, okay? And it contains tiny drills. So we're going to produce a hole using a tiny drill. What do we use here? How about we use a number 76, which is 20 thousandths of an inch in diameter. And for that, we're going to use our small drill press. Now, I would normally use an even smaller drill press for such a small drill bit. This is the smallest I have. So I'm going to use a double chuck, a manual chuck. So if you look here, I have my normal drill chuck, and in that drill chuck I have mounted a second drill chuck, which can be fed into the workpiece manually. And we'll see why that's important. Now, when you take the drill out of the index, make sure that you use a white tissue paper, because drills that are that small are easy to lose, and if you drop it, Especially if you drop it on a machine tool where there's a chip pan, you might as well go get another one because they're very difficult to find. Now, one important thing is before you use a drill and before you use any tool, inspect it. I don't know how many times I've seen people screw up a job because they didn't inspect their tools. And that goes for brand new tools as well. I've seen on regular or on many occasions tools brand new that don't have the proper cutting geometry. So inspect, very important, especially with taps. Okay. And this one looks good to go. So I'm at the workbench and I've set up to drill that small 20/1000 of an inch hole. Now 20/1000 of an inch, that's about the width of 7 hairs. And that's not very much. To give you an impression, here's a picture of the drill with a ballpoint pen, and that'll give you some idea of its size. So it's very small. And what I'm going to be doing here is drilling that hole in this piece of half-hard brass. Now I've backed the half-hard brass with a piece of nylon that the drill will penetrate once I come through the part. It's important to back it with something so we have support. I don't want this small part over the hole in the center of the table because it won't have that support. So I've backed it here and that's okay. But as you can see right here, I don't have my 20/1000 of an inch drill. I have a, I guess that's about an 832 taper tap. I'm not going to tap any holes, but remember, drills don't track on their own. They have to have something to start into. Now we can spot drill, we can center drill, we can punch. But for this smaller hole, I have to punch with a part that's stationary already in its right position, because I can't use the drill here to center on the punch mark. The drill is too delicate. So I've used this taper tap to come, since it's pointy, and make a small, it doesn't need to be very large, we're talking about a 20/1000 of an inch drill, a very small indentation, just like that. All that's required, and that small indentation will guide my drill to the proper position. And now, without moving anything on the machine, I can pull that taper tap out of the chuck and replace it with the drill bit. And now we can start to drill. Well, when I see the nylon chip coming up, I know I'm well through the part. So that's drilling a 20/1000 of an inch diameter hole. Now, let's take a look at the result. And there you can see, it's pretty tiny. Now, there's true limitations to drilling these tiny holes. You cannot drill 1 inch deep into a part with a drill that measures only 20/1000 of an inch in diameter. Think about it. When we looked at drills and drilling, different types and how twist drills function, we mentioned that you should not drill continuously more than 3 times the diameter of your tool. After that, you have to get into a peck drilling cycle. And there's problems with clearing chips when you get this small. So really, you want to drill small holes very shallow. You don't want to drill deep, small holes. And also, I mean, the small holes aren't necessarily on tiny parts. So if you're using a tiny drill press, and this is by far not the smallest I've ever used, which was about this tall, well, there's true limitations on the size of part that you can put into a machine like that. So what can you do? Well, you can cheat, and that's what we always did. When we used to drill these small holes, oftentimes it was for pressure holes in wing surfaces on models for the high-speed wind tunnel that I used to work for. And we used to drill these small holes in sequence on the wing to get pressures at different areas when it was mounted in the tunnel. And that's a problem because most of those wings were made of 17.4 hardened stainless steel, 17.4 pH, I think it was H900. So that's not important. What is important is that we cheated. And to cheat, well, we would drill larger holes into the wing, counter bore those larger holes. They weren't huge, but they were larger. And then we'd turn plugs, brass or whatever, that we would then drill with these holes and press fit into those larger countersunk holes and then finish them flush. Let's go over to the whiteboard and take a look at what I'm talking about. It's really quite simple. We have in this example a part of somewhere around 3/8 of an inch thick of hardened stainless steel, and I've shown it sectioned with the cross hatching just so that you can see the hole going on inside. Now, the objective here is to produce a 20/1000 of an inch hole in this very tough material, and I'm not going to manage to make it all the way through. So we used to drill a larger hole, let's say in this case somewhere around 1/8 of an inch, and then counterbore that hole. Now that gave me my throughway through this tough part. And then I produced a smaller, or a press fit plug in a material that isn't as difficult to drill, and I drilled that plug with the 20/1000 of an inch drill. And that way I get my hole diameter and I have my through hole, and I don't have to drill very deeply into this very tough stainless steel. So here we have the long and the short of it. We can compare easily by putting one next to the other, this combination mill and drill and this small benchtop drill press. Now, what's the main differences between both? Well, visually, the biggest difference is that the combination mill and drill, well, has this XY axis table. So the table can be moved very accurately in both the X and the Y axis. Whereas the drill press has only one axis. Now they both have this one axis, which is the quill or the spindle axis. And that's required for drilling. Now that's important because that is visually the most obvious difference here. But the real difference, I mean what really matters, is what you can't see right off the bat. And there's two things there. First is the overall design. This machine is massive, okay? This machine is quite delicate. I'm not just talking about size, I'm talking about how it's designed. And the second main difference that you can't really see, well, are the bearings in the spindle of both machines. The bearings in this combination mill or drill are conceived or designed to take axial thrust, so a thrust that is parallel to the axis of rotation of the machine, and lateral thrust, or a force applied on the spindle laterally, perpendicular to the axis of rotation. So this spindle is made for both types of force, whereas the spindle on this one is really only designed to take axial forces, so parallel to the axis of rotation. Now, why would I go out of my way to explain that? Well, there's an important reason, and that is that sometimes people get ideas. Now, most ideas are good, but sometimes ideas are really bad. And one idea that comes up fairly regularly with owners of especially wood shops, because they don't really need a mill often, is to get a small drill press and to add to the drill press a X and Y table. And you can buy these tables in most machine tool stores. You still won't get a small mill. You're going to get something that could be dangerous. Now, it may work if you're making very light cuts in very soft materials, like if you're cutting wax or something like that. But really, it's not a good idea because first, the bearings aren't made for lateral thrust. Fine. But on top of that, I mentioned the structure of the machine is not designed for it. And that's a little hard to wrap your head around because they look so much alike. Well, let's look at just one of many differences between the two, and let's look at how the work head of each machine is fixed to its column. So here obviously is the head of the small drill press, and I can see the column right here. And what do I notice about holding the head onto the column? Well, all I have to fix it in place are two set screws, 1 and 2. And these set screws screw directly onto, but not into, onto the column. So it's that friction, that force applied by two set screws that holds the head onto this column. And here we have the setup for the combination mill and drill, and we can see the head and we can see the column. And we can see that we have two massive bolts and nuts holding the head onto that column. But the main difference here is that these bolts are not applying their force onto the column. These aren't set screws, they're bolts. What they are doing is they're tightening a split sleeve. And that means that when I tighten these, the head contacts the column on a very, very large surface. And that means that this will really fix this head to the column in a very powerful and accurate way. I'm sure that many of you know this type of clamp. Here's a 3D effect. Ooh, scary. Okay, so these are, well, they're a type of strap clamp really, and we can tighten them down and they hold quite positively because they contact on a very large area. And that's basically what this mill drill is doing to hold the head onto the column. A very positive way of fixing the two together. Now, some people might say, well, I have a bigger drill press than this. Well, I do too. So let's go see a drill press that's about midway between this small bench top and this combination mill and drill and see how it's fixed, or the head of that drill press is fixed onto its column. So here we have my intermediate drill press. It's about halfway between the size of that small bench top and the combination mill and drill. And what do I notice here? Basically the same setup. And if I look here at what's holding the head to the column, I have 1 and I have 2 set screws. Exactly the same setup that I had over on the small bench top model. Now, there are many, many types of drill presses. Now, the amount boggles the imagination. But our objective here is to describe this type of machine tool. And for that, we're going to simplify things down to 3 basic types. The small bench type or bench top type sensitive drill press, larger and more powerful pedestal type gear drive drill press, and a very large radial arm type drill press. So, 3 basic types of drill presses. We have our sensitive drill presses, we have our gear drive or gear head drill presses, and we have our radial arm drill presses. And this is a typical example of a small sensitive drill press. Now, this is not called a sensitive drill press because it gets upset easily. I mean, this drill press isn't going to cry if I see or use my other drill press more often. And if I forget the date at which this drill press came into my life, well, it's not going to get upset. It's not sensitive in that way. No, it's called a sensitive drill press because it gives back to me a lot of information when I use it, because it's sensitive to the touch. But why is it sensitive? It's not just because it's small, although its size does have something to do with it. Small machines accumulate less energy in their movement or their moving parts, and that gives me a better sensibility when I use it. But it's not just that. It's also things like the pressure on the spindle return spring. On these machines it's quite light, and that increases my capacity to feel what's going on. But more important than those two first things is the fact that these machines are belt driven, and belts drive my spindle very smoothly, and they don't impede my capacity to feel what's going on. Now, belt drives are quite smooth, especially at high RPMs, but they have a drawback, and that is belt slippage. So that's the negative point of these machines. We get a lot of belt slippage. Now, why is that important? Well, it's not good for large tools, obviously, because we can't transmit as much torque to the part. But it's also a bad thing if we want to use power feed on a drill press, and that's why these sensitive drill presses never have power feed. But why is it that belts work better on small drill presses and that large drill presses require gear drives or work better with gear drives? It's a question of tool size and feed, really, because when I'm using this type of drill press, my cutting pressure is quite low. I don't really have to push with great force on the lever to get a nice cutting action. And on these small machines, I'm going to adjust my feed, my manual feed, by applying pressure and observing the chip being formed and seeing that my chip is a nice formed continuous chip. Okay, fine, I can do that with this machine because it is quite small and sensitive. Now, obviously, if I'm using a 1-inch drill bit and I'm drilling into a large plate of steel or a thick plate of steel, I'm going to need incredible amounts of pressure applied on the tool to get a proper chip to lift from that cutting tool. And that is a problem, because when I really have to push down with force on a lever, I lose sensitivity. But there's more than just that. We mentioned belt slippage. If on this machine with manual feed, the belt slips somewhat, and it always will, well, it's not a problem because I'm adjusting on the fly and I'm noticing what's going on, and I can feel in my hand what is going on, and I continuously adjust my pressure to get that proper cut. Now, when I'm cutting with a large tool, that won't work. We need power feed. Power feed is really reserved to gearhead machines for one basic reason, and that is, can you imagine the mess you would get yourself into if you were power feeding a drill into a hole and that your drive belts for your spindle started to slip, but that your feed drive didn't? That would be a disaster. Now, I don't have an example in my shop of a gear drive or gear head drill press. So here's a picture of a nice Grizzly drill press, and as you can see, it's quite massive. Okay, it's made to really cut large holes with large tools. It does have a power feed, and that's important, and it is a gear drive. So this is really a drill press that you'd use for big jobs or for drilling large holes. Our third type of drill press is the radial arm drill press. And it's sort of like a gearhead drill press with one major difference, and that is that it has a flying head. And that head can be moved up and down or back and forth along an arm that moves radially around the column. And that's why we call them radial arm drill presses. So why is it important to be able to move that head around? Well, it's because radial arm drill presses are massive, large machines that are made to produce large holes in large parts. Now, we know that on most drill presses, except for the radial arms, we move manually the part around the table to position it for the drilling operation. And that's fine with most parts, but if you're going to be producing very large parts, well, that becomes a problem, because these large parts are going to need to be clamped to the table to use large tools on, and you don't want to make a setup for each hole that you have to drill. So you don't want to move the part. So on very large parts, you're going to fix the part to the table and move the head around to the different positions. Now, this is a radial arm type of movement. So it's circular and linear movement. It's not an XY. You cannot use a DRO for this type of machine. So it's still a drill press that's positioned almost exclusively visually, but its head can be moved. So you don't have to be moving a very large part all over the place. So 3 basic types of drill presses for 3 very different situations. But there's no law here. This is just 3 examples of 3 what I consider to be basic types. You can mix these up as you want, and there's, as I've already mentioned, hundreds of permutations. I mean, there's all kinds of drill presses out there. And we can see just in my little shop that I have a small benchtop drill press here. I have one that's about twice the size and twice the strength over that I've mounted on a base, and I have that combo mill and drill that really isn't a drill press, it's a hybrid machine. So, drill press types. It's just a way to sort of figure out what you need for the job that you're going to perform. That's about a half hour for this part 1 of our lesson 8. We'll meet in part 2 where we're going to be looking at our 6 basic operations that can be performed on the drill press. And until then, have fun, be safe, and happy machining.
You